All right, we're on. So this, just to clarify for the folks at home, is the first part of the Kinetics and Equilibria topic. So if you're year 13, you need more stuff on KP and Arrhenius, but this is just the year 12 stuff. Okay, so we start with the Maxwell Boltzmann distribution. For drawing up Maxwell Boltzmann distribution, you've got to know the whole thing. You should know the labels on the axes, which are
kinetic energy of particles.
I'm just going to literally whittle that down to energy. Is that all right? But kinetic energy of particles is a perfect answer. And up here?
Frequency.
No, it can't be frequency.
Number of particles.
Yeah, number of particles is the best answer. Frequency means something else. It's something per time or something per volume. Okay, and then your line has to start at 0. There has to be a bulge somewhere at the top, and then it has to come down. It looks like it joins my arrow there. It has to come down towards but never touching the x-axis there. Okay, so just a couple of important things to notice. Thank you. The most probable energy is just the top of the bump there, whereas the average energy will always be slightly to the right of that. I might have exaggerated that a bit, but you get the idea. Slightly to the right of that because the graph is asymmetric. It's anchored at 0 over here, whereas it can extend to higher and higher numbers over there. Okay. If we change the conditions a little bit, if I can just, we have a number. If I increase the temperature, this will be T1. So if I increase the temperature, what happens to the graph?
It gets like the top goes lower.
Top of the bump goes lower and
it only passes through the line 1.
it does pass through line 1, yes, but it's lower and think about what happens to the average kinetic energy of particles if I increase the temperature. It increases, yes. So the average increases, so the bump must be a higher energy as well. Okay, so the bump is lower and to the right. Again, both graphs start at 0. They should only cross once, and they should be left hanging above the x-axis. So we can use this as a way of explaining why increasing temperature increases rate. If I put my activation energy on there, the activation energy EA, then only particles that are equal to or greater than or equal to the activation energy can react. At a higher temperature, I will write this down, at higher temperature, many more particles have, and what do we write? Energy greater than or equal to activation energy. And that's a much more appropriate response to the question, why does temperature increase rate, than is an increase in collision frequency, because actually the collision frequency hardly goes up at all for an increase in temperature. Whereas when we look at how many particles are above the activation energy, it doubles for about every 10 degrees increase in temperature. So we get that appropriately exponential graph. Okay, the other thing that we could show on this graph, I'm going to show it on this one over here, is if we had the activation energy there, what happens if we add a catalyst? John?
The activation energy is lower.
Yeah, so there we are, with a catalyst, the activation energy would be lower, so again, more particles are over that line. More particles again have energy greater than or equal to the activation energy. Is that everything? Oh, one more little detail. What is the area under the graph represent?
All particles with energy.
So that would be all particles. Yes. Okay. So it's the total number of particles. So if I double the number of particles but get the temperature the same, then what happens to the graph? Double the number of particles,
The area,
keep the energy the same.
area, and the graph.
Not about being steeper. I mean, it might be steeper. What happens to the graph if I have twice the number of particles but at the same temperature?
Doesn't it just go higher
It would go higher.
and then still be the same? Yeah, but I don't know how to explain.
Use words.
Most probable energy would be higher.
No, it wouldn't be higher. Most probable energy would be the same.
Stay the same.
Yeah, if it's the same temperature, but the average kinetic energy of particles is what temperature is. When you're measuring temperature, you're measuring the average kinetic energy of particles. Although that seems miraculous that you could do that with a glass rod with a bit of mercury inside, that's what you're measuring. So if the temperature's the same, then the average kinetic energy must be the same, so the bump must be in the same place. Not that my finers work. There we go. Okay, so I've got twice as many particles, so I've got a bump which is twice the height, but the middle of the bump, the top of the bump, should be, what colour was it last time? Brown. Should be in the same place. Again, not my finest work, but you get the idea. If you don't get the idea, then rewind and listen to it again. Okay, so just a recap of those sort of GCSE type questions. Why does rate increase when temperature increases? So we say, someone give me an answer to that. Why does rate increase when temperature increases?
More successful frequent collisions.
We don't say that.
Oh.
We say this.
Oh.
Why? It's written on, the answer's written on the board. Why does rate increase when temperature increases?
Why does rate?
That was what I said. Go on.
At higher temperature, many more particles have an energy that is greater than or equal to activation energy.
Okay. Okay. Yeah. Stay. I know that the collision frequency thing was very much drilled into you in GCSE, and you know we've got to get you through one exam before we can get you through the next. But it's not really the explanation. I mean, it's not untrue. It's just not. It's not the phenomena that explains what's going on. Why does rate increase when we increase concentration of a solution, obviously?
Because this increases the number of particles per unit volume.
Increased number of particles per unit volume. Well, remember the Go, just finish it while I write this on.
This increases the collision frequency, which gives an overall increase in rate.
Okay. And the same for an increase in gas pressure. It's the same situation. You've got more particles in the same volume, or more particles per unit volume, or more particles per decimeter cubed, however you want to say it, which increases collision frequency. Okay, nothing to do with energy, remember. You're just squeezing more particles into the same amount of space. They're going to hit each other more often. And then the important thing to remember for solids is, well, usually this is the answer. So let's ask the question: why does a powder react faster than lumps of, I don't know, zinc? Why does zinc powder react faster than lumps of?
Larger surface area.
Yeah, so larger surface area, more particles are available to collide. It's a good way. So increased collision frequency. And we've already talked about adding a catalyst. You've got a lower activation energy, so again, more particles have energy greater than or equal to the activation energy. All right. Yep, grand. What's to do with that? Blue roll. Any questions on Maxwell Boltzmann or rate kinetics? Reaction kinetics, by the way, we talk about reaction kinetics, that's just a fancy word for rate of reaction. A workout cleaning a board. Probably never thought of this, but it takes effort. Yes.
Who actually was Maxwell Boltzmann?
Oh, I think it was two people, wasn't it? Google him. Right. Moving on to talk about that was the kinetics. So the equilibria part. We always need a context for this, so it's helpful to have good old Haber process on the board. First of all, when we say a system is in a state of equilibrium, what do we mean? Or dynamic equilibrium. We don't have static equilibrium in chemistry, but go on.
The rates of forward and backward reaction.
Okay, so
Or equal.
rates of the forward and reverse reaction are equal. So in other words, we're making product as fast as we're making reactant. A bit more?
The concentration of reactants and products remain constant.
Okay, so that remain constant is important there. Reactants and products. So they don't have to be equal. You could have 99% product and 1% reactant. The important thing is if you came back an hour later, it won't have changed. And in order to maintain this equilibrium, we have to be in a...
Closed system.
Okay, what is a closed system?
Like where nothing can get out or get it.
Nothing can get in or out, including...
The reaction.
And including... Not air. Reactants, products, and energy, including energy. I mean, that can't possibly exist, right? You can't have a system where nothing can get in or out, including energy. But as far as chemists are concerned, you can't have an equilibrium if you don't have a closed system.
So equilibrium can never be achieved.
Not really, no, but you can get systems which are close enough to it that we can, that the equations work. I mean, the thing about chemistry, it's a science, so it constantly battles with the real world. We model things in chemistry in a hope to predict how real systems are going to work, and they're never going to be 100% the same. But if they're 99% the same, well then that's usually good enough. Yeah. Okay, so let's go back to those changes in conditions. If we change temperature, let's go for an increase in temperature. How does an increase in temperature affect? Well, we normally talk about equilibrium position. So we can imagine that my reaction could be sort of 50-50, or the position could be towards the products, in which case we're making more products, or it could be back towards the reactants, in which case we're not making very much product at all. So we have this idea of the equilibrium position shifting forwards or shifting backwards. Or we can talk about the equilibrium yield, which is, well, you know about yield. It's the percentage of the mixture which is product. So we could have the equilibrium yield of ammonia, meaning what percentage of that mixture is ammonia? Is it 90%? Is it 10%? How much ammonia is there? So what's the effect of increasing temperature on the equilibrium yield of ammonia in this era reaction? Go for it.
Would increasing the temperature decrease the yield because it has to shift in the endothermic direction?
Okay, so it shifts the equilibrium, always shifts the equilibrium in the endothermic direction. So remember that if a reaction's exothermic forwards, negative delta H is exothermic. If it's exothermic forwards, then it's endothermic backwards. So in this particular case, if I increase the temperature of the Haber process, it'll actually shift the equilibrium position backwards. I'll make less ammonia, or less of my reaction mixture will be ammonia. Okay, just to add a little bit more to that, in terms of Le Chatelier, why does that happen? Why does an increase in temperature shift this equilibrium backwards? Just before you give me that, I'm sure, very good answer, could somebody just remind us of Le Chatelier's principle? I'll start you off. For a system in a state of dynamic equilibrium, a change to the conditions will shift the position to minimize the change. So again, that's what you take into the exam with you. You have in your head that Le Chatelier is about minimizing the change to any conditions. So why is an increase in temperature, why does the equilibrium respond by a shift in the endothermic direction? Go for it.
Because an increase in temperature will cause an increase in energy.
Yes.
So if you shift towards the endothermic direction, it will reduce the energy and minimize the change.
To absorb or to reduce is a good word. The extra energy or the added energy or whatever. So that statement there comes directly from Le Chatelier. Whenever you're answering a question where you're applying Le Chatelier's principle, you must put the Le Chatelier kind of bit, explanation, into your answer. What happens to my equilibrium position if I increase the concentration of a reactant? Say nitrogen's very cheap, 78% of the air is nitrogen, so that's fine. So if I stick in as much nitrogen into the reaction mixture as possible, how does the equilibrium respond to that?
Shifts to the right.
Shifts to the right to
reduce the additional reactant and minimize the change.
Okay, and the other important one you need to know about is a change in pressure. Let's stay with increase for the moment. How does an increase in pressure affect the equilibrium position? Go for it.
Shifts to the side of fewer moles of gas.
Side. I've just been just been marking the year 13 papers. There was a Le Chatelier question exactly like this, and yeah, I had a lot of people saying it goes to the side with fewer atoms, goes to the side with less stuff. Fewer moles of gas, please. Fewer moles of gas. Why does it go to the side with fewer moles of gas? Yeah, so to reduce the pressure is fine. Okay, again, so each time we're bringing Le Chatelier into the question. It's not enough just to say the equilibrium position will shift to the left because it's the endothermic direction. You might get a couple of marks for that, but you must include a statement which connects with Le Chatelier. Just before we move on, that idea of optimum temperature. If increasing temperature gives us less ammonia, why is the reaction done at 450 degrees?
The higher the temperature, the rate of reaction will increase.
Right.
So
the higher the temperature, the rate of reaction is faster, but I'm making less ammonia. But I'm making less ammonia faster. So there's two things in direct conflict with one another. The rate of the reaction and the amount of ammonia, or the percentage yield of ammonia that I'm making. And 450 degrees is a... Yeah, I use that word optimum, or compromise between rate and yield. That idea that if it was any cooler, the rate would be too slow. If it was any hotter, I wouldn't make enough ammonia. So 450 degrees is like a sweet spot. What about pressure then? Because increasing pressure increases rate, and in this case increases the equilibrium yield of ammonia. So why is the pressure only 200 times atmospheric pressure? Why not 300 or 1,000 or 10,000? Because an increase in pressure is always, what were you doing there? An increase in pressure is always going to give us a win-win in terms of rate and equilibrium yield. Go on, John, give us your answer.
Too expensive.
Just be very careful with expensive without a qualification. There's very rarely a mark for saying it's more expensive. Expensive because...
Well, it costs more to produce more pressure or something like that. I don't know.
Cost of what are we?
Energy.
Energy, yeah, is the essential thing. It would cost more in terms of energy and equipment. The containers would have to be that much thicker and therefore more expensive and so on. So actually, whatever conditions we have is always a compromise, because we're always, as a chemical engineer, we're always compromising the cost of staff and the cost of health and safety and lots of other things as well, I'm sure. Increasing the concentration of reactants shifts the equilibrium to the right. How do chemical engineers make sure that the concentration of reactants is as high as possible in the Haber process?
Not use a catalyst.
Well, we do use a catalyst. I'll come back to the catalyst in a moment. Okay, let's ask the question the other way around. How do we make sure in making the ammonia that the concentration of ammonia stays low, which drives the equilibrium to the right as well? Because if I decrease that concentration, the Chatelier says equilibrium will shift to the right as well. How do we keep that low? What was that, Adam?
Abdullah said you remove it.
You remove it is exactly right. Do you remember how you remove it? What was that?
By filtering it out.
Filtering's not quite right. You cool it and use the fact that ammonia, with its stronger intermolecular forces, what kind of intermolecular forces does ammonia have? Let's try that again. Hydrogen bonding, because it's got NH bonds in it. N2 and H2 only have van der Waals forces, but NH3 with its much stronger much stronger hydrogen bonding intermolecular forces has a higher boiling point. So if you cool down the mixture of gases, the ammonia will liquefy first. You can then remove that easily and leave you with nitrogen and hydrogen, which what happens to the leftover nitrogen and hydrogen? Recycle it back. So that increases the concentration of nitrogen and hydrogen going on. A catalyst doesn't affect equilibrium position. Why not?
So all you do is just make sure there's more particles in the reaction.
Yes,
It doesn't actually
but it increases rate though, right? Michael?
It doesn't change the condition, it only changes, like, it only shows the activation.
But surely, just take devil's advocate, if I'm making nitrogen and hydrogen into ammonia faster, surely that should increase the equilibrium yield of ammonia. No, because
You're not producing more reactants. You're still producing the same amount of reactants.
What's the question, sir?
Oh, because it speeds up the forward and backward reaction at the same rate.
okay, equally is a good word there. Right, so my point was, if we're making nitrogen and hydrogen into ammonia faster, surely that should increase the equilibrium yield of ammonia. And the answer's no, because we're turning ammonia back into nitrogen and hydrogen faster as well. In other words, a catalyst speeds up the rates of the forward and the reverse reactions equally. If it doubles the speed of that one, it doubles the speed of that one as well. So it doesn't actually change the amount of ammonia that I have in the system. Whew. We're not there yet. What do we got? Sun time. Right. KC. Oh, I shouldn't have rubbed off my reaction, should I? How do I write the expression for KC? Do you remember when AQA asks for an expression, they mean something mathsy, as opposed to an equation, which is something chemically, chemistry-y.
You want the square bracket Square brackets meaning concentration.
So for Haber process,
Square brackets spread.
yeah. So key things to remember is product goes on the top. The substances go in square brackets, which means concentration of, that's why it's Kc, that little c there is for concentration, and then raised to the powers of, yeah, the balancing numbers, or the moles in the mole ratio in the equation. Huh? Yeah, products over reactants. If I was to work out the units for this particular Kc for the Haber process, how would I go about doing that? Yeah, so I know that concentrations measured in moles per dm cubed, and then I have to take into account the fact that there's powers in there, so we'd end up with moles per dm cubed squared on the top, with moles per dm cubed times mole per dm cubed cubed on the bottom, which then needs some simplifying. Go on, Adam, go on.
You can cancel one off the bottom and then one off the top. And then you get. You can cancel that again. That becomes.
Okay, so 2 off the top, cancel 2 off the bottom. Now what?
Expand the bottom.
So it's 1 over.
Mole to dm minus 6. And then
Okay.
that turns into
1 over mole squared is.
mole to the minus 2, and then dm to the plus 6.
Okay. So for Kc, we have to work out units separately for every different reaction that we've got. So it's a fairly standard question. Let's move that over here. Yes. Sorry, the Chatelier. Come on, you. Oh. Ooh. Okay, so let's imagine that we're doing an experiment, and we're going to start off with, let's have 5 moles of nitrogen added to 2 moles of hydrogen. I've done this before, and people have said, no, hang on, shouldn't it be 1 of those and 3 of those? Well, it doesn't have to be. I can put as many moles of gas in a box as I like. Yeah, we're in charge. And I'll leave that going for a bit, and then when I come back later, I've made 0.6 moles of ammonia. Should we go 0.6? No, let's have 1.2. Come on, let's make it more interesting. Is that all right? That's all right, isn't it? Okay. How much nitrogen and hydrogen do we have left if I've made 1.2 moles of ammonia? And what's my tool here to work this out? Ice is the tool. Okay, so ice stands for initial change equilibrium. Great. So initially I had no ammonia, 5 moles of nitrogen, 3 moles of hydrogen. So what can we add to that now? Yeah, so that's obviously gone up by 1.2. So how much has the N2 gone down by then?
0.6.
Why 0.6?
I was thinking because there's two different reactants, so you split it. Because this two whatever react with each other, so you split it.
Okay, that's the wrong answer.
Is it based on the balancing number?
It's based on the balancing number. So what? How much hydrogen has been used up?
3, 2. I don't know.
These okay. The key is that these numbers here are in the same ratio as the balancing numbers, which are 1 to 3 to 2.
Yeah.
So
Oh.
the green numbers, as I'm doing them, have to be in a 1 to 3 to 2 ratio. So H2 must have gone down by
1.8.
perfect. Okay. So now we get our answers there. So I've got 4.4 moles there, 0.2 moles there, and 1.2 moles there. So we can now stick that straight into Kc, or is there something else we need?
Yeah.
What else would I need?
Your units.
These are moles. These are concentrations. So I would need volume. Okay, so let's make it a nice simple volume of 2 decimeters cubed. Could you work out a value for Kc for this reaction, please? Okay, so you should have products on the top, the ammonia is on the top, so it's 1.2 over the 2. Moles over volume is concentration, and then we need to remember to square that, and then that's over 4.4 over 2 and 0.2 over 2 cubed, which is, what did you say? 163, let's round it to 164 to 3 sig figs, although the data is actually 2 sig figs, but that'll do. Mole minus 2 dm plus 6. There's one little thing I forgot.
Why do you do that? Why do you do that? Yeah, why try to see what try to
I don't want to
So why do you do it?
There's a fairly standard procedure that you should know from maths and physics, which is to do with finding rate. If I've got a graph of, well, I've put the concentration of a product because that would be how you would measure it properly in a chemistry experiment over time. How do I measure the initial rate, or the rate at any point really? The presence of the big ruler should help. So if it's initial rate, we draw a tangent from the start, from 0. So I put the ruler on 0, and I draw my tangent there, and then I work out rise over run. Hang on, sit down. If the units were, time was in seconds and concentration was in mole per dm cube, what are the units of rate? Mole per dm cubed per second. Grand, that's good. Well done, folks. I'll put that up on Satchel now.